Hi all, I am Akonjola Ogunleye from the Perception and Language Lab at Virginia Tech and the University of Illinois Urbana-Champaign. Today I'll be presenting our work on 3D VCD embodied hallucination mitigation in 3D LLM embodied agent through visual contrastive decoding. Embodied agents are increasingly using LLMs as a reasoning core. They use it to reason, to make decisions, and generate plans towards a goal. For example, if we tell an agent to obtain a milk from a fridge, the agent might use LLM to generate a plan. Or the plan could be take this number of steps, open the fridge, take the milk beside the eggs. However, they tend to inherit the hallucination tendencies of their backbone foundation models. This makes them prone to hallucination. And the problem of hallucination is very critical. In this research work, we asked two fundamental questions. One, can we mitigate hallucination in embodied agents without retraining and doing this at inference time without extra computational overhead? Number two, if we need to perturb the same information of embodied agents and perform contrastive decoding, what kind of scene information do we need to perturb? We develop and introduce 3D VCD, the very first inference time visual contrastive decoding framework designed to mitigate hallucination in embodied agents. Here we present an overview of our 3D VCD method. Given 3D environment observations, 3D VCD builds a structured 3D scene graph encoding object categories, centroids, and extent. Our method then creates a distorted version of this scene graph as a negative context by injecting semantic and geometric perturbation. We then perform contrastive decoding on both inputs before generation, such that hallucinated generation is suppressed and correctly grounded tokens are amplified. For example, on the right, when X asks about the presence of a TV in the room, our method was faithful in grounding the question to the 3D scene and providing the right response. More details about our method can be seen in our paper. Here we show the quantitative result of our 3D visibility approach on the 3D pole benchmark. For more details on the other benchmark we considered, we refer viewers to our paper. Across all three the pop evaluation settings, random, popular, and adversarial, our method achieves the highest overall performance, consistently outperforming existing 3D language models along every metric. These improvements demonstrate that contrastive evaluation of original and perturbed 3D context effectively suppresses hallucination-prone responses and produces more balanced, faithful predictions. We wanted to test whether different scene graph distortions have any effect on the performance of our 3D visibility framework. And in order to isolate each scene graph distortion contribution, we run experiments with one corruption type at a time. So sometimes we introduce semantic perturbation, other times we introduce geometric perturbation. For example, here logium would mean geometric distortions with little noise, and IGM would mean geometric distortion with more noise. And across all distortion types, our method 3D visibility consistently outperforms the baseline model by a substantial margin. For example, if we look at the random setting, the baseline accuracy score here is 63%, and our method accuracy ranges from 74% to 77%. So we substantially outperform the baseline method. And then these gains demonstrate that controlled perturbations of the object-centric 3D scene representation reliably strengthen grounding and suppresses hallucination. And we show a qualitative example on the 3D pole benchmark. Here, the baseline model incorrectly predicts the absence of a dining table, which is actually present in the scene, and then our method correctly grounds and identifies the dining table. We show another example on the ill benchmark. Here, agents were given a goal to check every sweater for lint and make sure none of them are dusty and put them on the bed. A very fine-grained instruction. The baseline model hallucinates a non-existent microwave here, and then while our method produces a clean symbolic goals with no hallucinated object. In summary, in this work, We introduced 3D-VCD, the very first training-free inference time contrastive decoding framework for hallucination mitigation in 3D embodied agents. And then we introduced novel distortion method. And then using this distortion method effectively suppresses hallucinated token while rewarding the generation of truthful tokens that are grounded in 3D scene. And finally, we demonstrated performance gains across several embodied benchmarks. Thank you so much for listening. Please join us on Sunday, June 7, 26 at 3:30 p.m. at Exhibit Hall A to hear our full presentation. And feel free to scan the QR code at the bottom of this page to have access to our full project page and our full paper. Thank you so much.